so it start to record. Okay, before the first session, let me just go through some okay, the question is set up an integral. Okay, so this is set up. Let me write here. Set up integral that represent length of the parametric curve. So it doesn't need to be calculated up until the exact value of the final results. Okay. Okay, so if we look at the questions, that it's supposed to calculate the length of the curve. So length of the curve, we can write as L, and then let's just write A to B, and then write the inside of the square root, it will be the first derivative of each functions, and then squared. Okay. So we can see that the dx over dt is 6t minus 3t squared, okay, and dy over dt will be 2t minus 2. Now we need to have some little bit calculations. From here we take the square, okay, because we want to find the square of both of these equations. And then let me write a little bit left. Now this will be 360 squared minus 360 cubed plus 90 with power of 4, and this will be 40 squared minus 80 plus 4, and we need to plus this 2. So we can write as dx over dt then put the square root up like that, so we can have -94. Let me arrange the power 4 and then 3, and then plus 40t squared minus 80 plus 4. If you look at the curve here, both endpoints, they will have at this y equal 3, right? Okay. So at y equal 3, we can look what is the equations. Y is t squared minus 2t. Okay. So we need to have or equal 3, and then we can set up our factorizations to know which t that is take the y equal 3. Okay. Right. So t will be from -1, and then t is equal 3. So the setup for the integrations will be from -1 to 3, and then we need to plug in all these numbers. Oh, okay. Okay. Actually, the question is asking using the calculators to calculate this, but I will just stop until here. I will give you one more question, and then we can move to the polar curve. So the idea behind the the parametric. Okay? It's actually all the calculus 1 techniques method, like derivative integrations. We are using the same techniques. Okay? Like for example, the integral or the arc length. What we are going to do is we measure, or maybe if you have the graph, you can graph and then look at the y-axis equation first. Okay? You can set up the integral if it's integration, maybe in x or in y, and then later you need to change to t. Okay? But at the first time you can write, for example, from x equals 0 to x equals 3, or from x equals 1 to x equals something. You can write like that first. But later, when you approach dt, you need to change the x into t. And it depends on the parametric equations. So basically, you are going to observe and calculate, or looking at the graph like just usual y and x. Okay? But later you need to change the endpoint into t. Okay? Like for example, this curve here, either we start from here or from here, we are having the same y equals 3, which means we need to know when they start and when they finish. If we think t as a time, right? When they start, when they finish, and because we are having our parametric equations here, then we can evaluate at which t that is having the same value of 3. Okay? And we get -1 and 3, and that's our endpoint for the integrations. Okay? So you can look on the graph, and then you can point out which value that we are going to observe, and then we are going to observe the parametric at the end here. Okay. The other example that I want to show you that is, I think, also considered as a typical problem in parametric. This is the equation of the tangents. Okay? So the question is asking the equation of tangents. Okay. But it's a little bit having, if in calculus 1 you are directly need to find the equation of tangent using the slope, and you can just plug in the points. Now you need to have another value, which is t, and then you need to match all the conditions. Like for example, the point coordinates of course is x and y. So at later calculation, you need to make sure that they are passing through this point, and you can plug in this x, y, and then find the exact value of t. The basic observation of the tangents in parametric is always we are going to have the dy over dx, because this is the key for the tangents, right? This is the slope, the gradient. And in the parametric, we will have dy over dt divided by dx over dt. Okay.
Just like use one of the x to the y, like put into the 4 inside the equation and you find the t, right?
Yeah, but that is for, you mean that
Yes, like
you put, for example, 4 here,
yeah, 4 here.
and 3 to be here.
Yeah, and you will find the t.
Yeah, but it's cubed and then it's squared, right? But either way, you can try first. Or you can directly try this and put into the equation first, which still includes t, and then you can later check whether that's true or not and match up with this x, y. That's also can be done. Okay? And I think that's more analytical, and I think more getting to the answer that we need. So if we look here, at least we know that this is our slope, our tangents for the equations, and we have our y and our x. We can set up the formula first. Dy over dt will be 60 squared, and dx over dt will be 60. So at least this tangent is just t. Okay. And then what we are going to do is we try to plug in this t into our desired tangent line. Okay. Our line will be y. Let me just write y minus y t, okay, equal dy over dx. This is x minus xt. Now based on our point, then this point will be our y and x, and this yt and xt is our parametric, and dy over dx is still in t. So we will try to find which t is possible for our condition. Okay? So we just have, this is 3 minus x is 4. Okay. Okay, let's solve this. 3 minus 2t cubed minus 1, or this will be 2. Mm. 4 minus 2 squared minus 1, so 3. So this will be 3. cubed minus 3t plus 2. We have some cubics. We can set some polynomial methods to find the roots. At least we will have 4 numbers that's possible: minus 1, 1, minus 2, plus 2. Let's start from, I think, negative 2. Oh, we get this. Okay. So we will have t plus 2, and then t squared minus 2t plus 1. This is, this, right? Okay. Okay, now we have this. So we will have t is equal 1 and t is equal negative 2. Okay, now from this t, okay, we'll go here. So we can have y minus 3 equal x minus 4, or y equal x minus 1. So t can be 1 or negative 2, and then we can write another formula here. So if t equal 1, this will be the result. If t equal 2, this will be the results. Oh, negative 2, sorry. Oh, wait. The negative 2, this is the same. So negative 2, let me just write here. Y minus 3. This is x minus 4. Minus 2x plus 8 plus 11. Oh, plus 11, sorry. Sorry, wrong. This is or y equal negative 2x plus 11. So this will be the answer. This one?
Because for the end result, t is equal to 1 or negative 2, right? But if we substitute negative
0. If you
negative 2 to the given equation.
to going back to the original tangent line.
The negative 2 to the equation, you will not get the v, but you will get 16. If we apply the negative 15. I think we could just like try to input the 4 into the x and then the t. And it will also produce the y equals x minus 1.
But because if we substitute t is equal to negative 2 to the given equation, which is x is 100.
Yeah.
t squared could become 15, right? So is it so would that be like breaking
The 15 one is actually correct, but it will ends up being this line. So what I mean here, okay. So first let me explain here. This is our approach for the parametric curve, right? Okay. We get to find what is t that is takes this into 0, right? We take on the t, which means that is t that we want to find, okay? That is this dy over dx, okay? And then we get two value of t, which is 1 and negative 2, okay? If you plug in this to our dy over dx, we get two tangents, we get two slopes. The first one is 1 and the other one is negative 2. We put on the tangent line that is in our equations for this 4 and 3, which is 1 minus 3, okay, and then the slope and then x minus 4. We can use the first one is being 1, which is directly we get this, and we get this equation. Secondly, we are trying to use this negative 2, which is this. And we get there 2x plus 11. Okay? That is how the line will be. Okay? If you plug in here, of course it will be not, if you check on this equation, of course it will be brings 0 to your evaluation.
I mean like in the given, because in the given for the value of x is equal to no, I mean in the given question.
Yeah.
No, like the question itself.
The-
X is equal to 3t squared.
Mm-hmm.
X is equal to 3t squared plus
Yes.
1, right? So if we substitute t is equal to 1, it will meet the requirement that x is equal to 4.
Yes, yes.
But if we substitute negative 2, it will become 13. So
If we put negative 2, what will happen? It's 15.
yeah, because
15, right?
yeah, because negative 2 squared.
Yeah, but will it still be cutting or crossing the 4 3? Yes, yes.
Oh,
It's been still the same. 15 is also okay, but it's crossing also 4 3. You can try to draw. It will cross this one. The 15 one will also cross this 4 3. Okay, I know you mean what you mean. Okay, this equations, right? Okay, it's still okay. You put negative 2. Of course, it will be 15. But the question is this a line? A line, right? It will cross the 15 and also cross 4 3. Draw. You can draw. So if you look on this 4 3, it doesn't mean that this is the only point. You got what I mean? This is a line. So of course there will be at least 2 points that crossing. Okay, one is crossing the y, while the other one is crossing the x. Okay. You can also look on this the other way around. What I can see what do we mean is y minus 15 negative 2 x minus 13, right? It's also the same line. Okay, same line with what my line here. Okay? So we have two lines, this the gradient with this which is 1 and the gradient which is negative. Okay, I hope you got my point. Yeah. Maybe later I will give you some maybe 5 or 6 exercise. Maybe later tonight I will try to post on Moodle, and let's see how you can deal with the questions. Okay. Still have any questions? You still have any questions?
Professor, may you explain us how can you achieve the equation?
You mean this?
Yes.
Oh, okay. Sorry, I've skipped this part. So basically, if you have this any polynomials, and you assuming that they will perfectly can be factorized, okay? Assuming that you can factorize perfectly, the first thing you need to see is the last number, and it's with like it has 2, right? And the first number, which is just 1. Okay. The possibility for the factors will be this divided by this. So we can call that P over Q. But this is not only the number, but it's the factor. Okay. The factor that made 2, it's 2 and 1, plus minus 1, plus minus 2. Okay. If you have, let me change this. Maybe this is 4. What 4 will be? 4 will be based on plus minus 1, plus minus 2, and plus minus 4. Because you can get 4 from 1 and 4, 2 and 2. And their combination of positive and negative, right? This is just a shortcut on how we can get the numbers easily. So from this 2, we can have at least these 2 numbers with each signs variations. Okay? Okay. The later part is trial and error using our division, our polynomial division. You can use, if you remember how to use this, okay? This is in a polynomial. I try to divide from negative 2, and then it takes this 0, which means that it's perfectly divided. There is no remainder. There is no numbers here. If there is number here, which means that it's not perfectly divided. Like when you divide, this is actually, you can write this as, let me change this. So this is divided with something here. It can be t plus something, or maybe t squared But I think it will be better if you just define using this syntactic sufficient. It can be defined by -2, 2, 1, +1, and etc. And you can find the results here. And it should be similar, okay? But I think this is more practical. So you put on the numbers, right? The numbers from the equations. There is no square, so we have 0, -3, 2. And then what we did is we are going to put 1 down, and then we multiply 1 with -2, -2. We add 0 and -2, multiply with -2, 4, plus this -3 will be 1. 1 multiplied by -2, -2 plus 2 is 0. Okay. And then this will be the results here. Okay. So the results we write as a, usually we say that as a quotient. So t plus 2, which means the t equal -2, is one of our root. And then the other part will be this t squared, -2t, and 1. We put here, and actually this is factorized, and becomes t minus 1 squared. Okay? And that's why we have the results t equal 1 and t equal -2. Okay? Anyway, I think there are several ways to factorize the cubic. This is just one way to solve. Okay. Okay. Any questions? Okay. I think we can move on. Okay. Last time we have the polar, but let me just take on another graph that last Friday I mentioned that we have 1 plus, let's say, sine theta. Okay, if we have the Cartesians, theta and r, okay. If we try to draw, let's start from 0, then maybe pi over 2. Okay. Because there is plus 1, then we start from 1. Let's say 1 is here and 2 is here. Okay, at least that is our graph. And then if we draw this into the polar, and let's say this is line theta equal pi over 2. This is line theta equal 0. And this is theta equal pi. Let's start from 0. 0, if we put into the equations r 1 plus sine theta, it will be equal to 1. Okay. So let's say 1 is here. And if you look the Cartesians, from 0 to pi over 2, we increase our radius, right? So if we imagine this is going to rotate like this, then the radius will change. So it's not a circle. So it's going to have like some additional length. Okay? Some additional length. up until pi over 2, we have radius is 2. Okay. So let's say this is 1, this is 2. Let's say this is our radius here. So we will have, let me just draw like this. Probably like that. Okay. It's not really curvy. Maybe I will change a little bit. Okay. And take the arrow like that. And then the graph, the curve, the radius will reduce. If you look this theta equal pi, it will reduce until 1. Okay. So it will be going back because it has a certain similar value, right? From here and here is the same, right? Up until 1, still the same. So it will be going back to here. So it has a symmetric shape, right? So let's draw that. So from here, going to have this symmetric shape. Okay, maybe like that. And now from pi to 3 over 2 pi, if we look, 3 over 2 pi is going to have 0 value. So it's going to be in the center of this axis, right? The polar axis. So it will be going to be here, and here, and here, because it's going to be decrease. So it should be less than this radius, right? Okay. So it's going to be like this, okay? And then from 3 over 2 to 2 pi, it should be the radius is equal 1. So 2 pi is actually going back to the 0, right? It's full circle. So it's going back to half this, and it's symmetrical. Once again, it's symmetrical. If you look, and if it turns this shape, it's like a heart, right? Like a heart. So it's called the cardioid. The cardio as in heart. Okay. It's called the cardioid. And as I mentioned, if you have 1 plus cos, it will be like this. If you have 1 minus sine, it will be like this. Okay. If you have 1 minus cos, it will be going to the left. And the family of the polar curve, we call this Limason. But I will not give you all the curve, how it looks like, and so on. I will only give you the idea, and then probably some video that is really helpful to imagine how the curves will be obtained. Okay. Perhaps one more graph of the polar, and then we can move to the calculus polar. Okay. Later, I will give you, I think, 1 or 2 videos to help you look on how to draw and how the polar curve will have some property. Okay. Especially how the patterns will be. Okay, the next curve is r equal cos 2 theta. Okay, we can draw the Cartesian first. The Cartesian. Start from here, going down to -1, and then turns back, going up until pi, then going down. Okay, now we have the Cartesian, and we need to transform these Cartesians into a polar. Okay, let me just finish the polar and then you can have a break, okay? Okay, this is theta 3/2 pi. Okay, now will be a little bit more complicated because we will have a negative radiance, which will, for some of you, perhaps it will be a little bit tricky. Okay? Because remember, the negative is actually, we consider there is no negative in a polar. The negative one is the opposite sign, right? So let's try to move from 0. So let's try from 0. We have equal 1. Let's say this is 1. Okay, and then we are going to have some decreasing value up until pi/4. Maybe I will draw some line here to denote the pi/4. And also for the other one. So this is pi/4. So at pi/4, it will be a 0. So it's reduce, and then going to be 0. And from pi/4, it's still decrease up until -1 here. So it's actually from here, from pi over 4 to pi over 2. But since it's negative, we are going to have the opposite sign. So it will be pi over 2 is negative, so it should be going through here. Okay. And when you have all the possibility, okay, from all the conditions, you will have this is perfectly going to be here. And there will be another one from here. And there's another one from here. And then there's another one from here. And it's perfectly like a flower. And it's symmetrical. So you start from this, going here, going here, going here, going here, going here, going here. Yeah, a little bit complicated at the value, but the result is actually quite beautiful, right? A flower. Okay, you can have some short break, but I think only 5 minutes. Okay, so before we start the calculus in polar, I will just give you some idea on at least the limason, because I think that's also a typical polar. So the limason, I take the, okay, let me check this. Okay, if you look here, okay, this is a limason that is a family of limason, 1 plus a constant sine theta. Okay. We already draw the 1 plus sine, right? C is equal 1, which is this one, right? We already draw this. Now, how we can tell or we can know what will happen if we change the constant, which means if I write the formulations like this, A plus B sine theta, one way to know is from the ratio of A over B. Okay. If A over B is equal 1, which means A and B is the same value, we will have this. If A is greater than B, we will have this, and this, and this. Okay? If we have the constant here is greater, or which means the B is greater than A, we will have some loop inside. We will have some loop inside. And if the constant is getting bigger, the loop also getting bigger. So you will see some evolutions here. So from here, going smaller, and it's going to just a point. There's no loop here, and then start to lose the 0. Start having like a curvy around here, and it starts looking like a circle. Okay. And still like a circle, but it's not a circle. If you look, this is different radius, right? So this is not a circle. Of course, if you have 0, it will be a circle with radius 1. Right? Okay. Like here, the radius is 1. and it's perfect circle. And when you have going to have like a minus, it will go a little bit down, and going down, and it's perfectly negative. I told you before, if you have the negative, you will have the mirror side of the positive one, and you have the, also another loop like that. Okay. Okay, so that is Limason family. For the details, I will try to give you some explanations in some video that I think I have watched some video that I think it's also better for you to watch. Overview of our polar. There is actually four type of curves. Okay. The first one is a circle and spiral. Okay. The spiral we can have if we have a constant and a theta. Okay. That's a spiral. And then limaçons, like we mentioned before. Limaçon with inner loop, cardioid, a dimpled limaçon. That is a small curve, and then a convex limaçon. Okay, like it's almost a circle. Okay. And then we have rows. And you see that there will be a difference when you have the number of petals is even and odd, and an even and odd. There are some patterns, and I will show you later how to find. If we have an even 2 theta, it will be the number of petals will be twice as much as this 2. But if you have an odd number, it's just the same petals. There are some factors on that also. But don't worry too much on the graph, okay? Because if I give you the exam, I will give you the picture. Okay? Because we are mostly focused more on the calculus. Okay? But at least to know and to explain, I will give you additional video later. And the latest one is the lemniscates. Okay? Lemniscate. There are just only two kinds. The first one is a squared sine 2 theta, and the other one is a squared cosine 2 theta. And there are just like this one and this. It's actually you just rotate this to there, going from here going to the right, pi over 4, because of the 2 theta. Because cos and sine is the difference is just only pi over 2. Because it has a 2 theta, then the difference will be pi over 4, right? So you need this exact to rotate pi over 4, and it will be the same curves. Okay. So only 4 types of polar curves, and I think we can move to the calculus in polar. Okay, to start, we need to first start from let's say we have some region like this. We have a radius, we have a theta. This is a sector, okay, sector of a circle, which means you have a circle and then you cut down like you take a pizza, okay, like you take a pizza. The area will be theta divided by 2 pi, because the whole circle, and then pi r squared, right? And it will be half, let's say, r squared theta. Okay. So we start from these equations. Okay. By using these formulations, we can set up our random region polar. Okay. So we set up our region, drawing the polar axis. Let's say this is the polar axis. And then let's say we have from there, and we'll have two angles. Okay. This is theta equal, let's say theta equal A, and this is theta equal B. Okay. So we have two angles, A and B. Okay. Or if I draw the angle, this is A, this is B. Okay. And let's say we have a random, let's say this is region R. And this will be our polar curves or polar equations, which is R are functions of theta. This random curve here. Now to find the area, we can set up our sector. Or first, we can set up our small region from the R. Okay, we can set up. Let me just erase this first, and then maybe take this and this. Okay, maybe that's small. Okay, I think small enough. Let's take this small region, the light green one, small region, and let's take the small angle as a theta I. So this is theta I minus 1. This is theta I. Okay, let's just to note that there will be a small angle, and the difference. Let's say we have a delta theta. And the average value will be f theta I, a sample point of theta. But just to note that this is just to express that we are going to evaluate this small value, the small value of the small region, okay, small region. So the small area will approximately going to have the sector area. The radius is f, and the theta will be the delta theta. Okay. And from the delta, we are going to evaluate the total area. So we are going to plus all the small region. And then as the small rectangle takes many shape here, so we can approach through our limit. Okay. So as n going to have or going to approach an infinite number, then we will have limit as n approaching infinite number of our sum and then if we set up this is from a to b, then we can set up the integral from a to b. Okay. Or we can write the area as integrations from a to b half r squared d theta, with r is functions of theta. Okay, so we can set up an integral that describing the polar as integration from a to b. A and b is our angle of half r squared. R is a functions of theta, and then d theta. Okay.
Professor,
Mhm.
a dumb question. How do we know the area is one half the radius times the angle?
It's from the sector here.
Yes.
So if we imagine this, okay, perhaps you need to going to have a smaller region.
Yes.
If you take this and take this as small as possible and treat this like a area of a sector, area of a sector of circle, you will get that this will be, we can approach with the sector, and then imagine this going to have some other small area as well, and that's why we are having the integral. Okay. Okay, let's take some example. Okay, let's take some example. Let me take here. Okay, find area enclosed by one loop of r cos 2 theta, the one that we already sketched, the flower. To give you the illustrations, let me draw the curve. Okay, so the question is asking the area enclosed by one loop. One loop means there are 4 loops in the curve. Okay. So it's actually asking this loop or this loop the same area. Okay. Let's say this is our one loop here. So it will be based on our picture. The area that we are going to observe is this. Let's say this is our area. So the theta will be from negative pi over 4 to pi over 4. Okay. We can say that this will be our formulations. Okay, and you can compute the area. But my suggestions, whenever you have a polar curve, which is usually symmetrical, you can take the half part of that, okay, and then multiply by 2 later on. Okay. So we can take this as just from 0 to pi over 4 of cos squared 2 theta. And then I think you can solve this. If you have the squared in a trigonometric, remember to change to the double angle formula. So I will leave this to you. Okay. So please try to solve. Yeah. And you can do it while also reviewing calculus 1. If you a little bit miss out on calculus 1, you can review to solve this trigonometric integrals. Because in polar, we will have so many curves that involves the trigonometric, at least sine and cos for the polar curves. Okay. Another notes that I think still important to have, if you have two polar curves in a one graph. Okay, let's say this is the curve 1, and we have another curve. Let's say this is the curve 2. Let's say this is f theta and the other one g, and this is theta equal a, theta equal b. And of course, from the graphs, we see that the f is greater than g and greater than 0. And 0 is between, b minus a is between 0 and 2 pi. So the area will be from a to b, and we need to subtract the f and g. But let me just write the whole formulations first. Okay. And then some notes for you. Remember that now we are in the polar curve. So how we are going to see the area is, this side is, let's say, the outer area. This is the inner area, and you will look like in terms of how large the value of the radius will be. That will determine which one is your top and your bottom equations in this one. which one is F, which one is G. Okay. And remember that you'll always start from this 0 and then you rotate counterclockwise. Okay. So this will be your first A, and then this will be your endpoint B. So A, B. Okay. Okay. Because sometimes the difficult part is when you have the polar and you treat them like you are using the Cartesians, and you end up with the wrong A and wrong B. Okay. Okay. Okay, we can have some example on this one. Okay, let's say we have 3. Okay. Okay, find area that lies inside the circle and outside the cardioid. Okay. So you have a circle and you have a cardioid. Remember last week we have done the circle to cos theta, right? Remember cos is positive, is going to be the right side, negative on the left side, and if you have sine, you will going to have positive on the top side, and the negative one will be the downside, right? So this will be a positive, so it will be going to be upside or top circle. And the cardioid, we already draw this, so obviously remember how. And it will cross or intersect with the circle, right? So if you draw, let's say that's our circle. Yeah, at least this the cardioid. Should be inside the circle, but outside the cardioid. So we'll have this. Again, we are going to have all the calculation will be done in the polar. Okay, so we need to find our intersections here, the angle from here until this one, so from the right here to the left. That will be our A and B, and the functions will be. This is the outside function, the 3 sine theta, and the inside one will be the 1 plus sine. So this 3 sine theta squared minus 1 plus sine theta squared, right? Okay. Okay. I think we can start to note the intersections. The intersection. So sine theta is going to be half, so this part will be pi over 6 and this will be 5 over 6 pi. So theta will be pi over 6 and 5 over 6 pi. So then we have half. Let me just write the whole formula first. This will be 3 sine theta and then square d theta minus half. Okay, and then we can evaluate all of them. And I think this is also symmetrical, and I think that is my suggestions for you. This is symmetrical at pi over 2, so we can evaluate until pi over 2 and then later multiply by 2. Because I think pi over 2 will be easy to be calculated later, right? So we can have area 2 I think you can solve this. I will leave that to you. Okay, because I think this is just a square, and then you can just use the double angle and then solve. Okay, there is one more sections about arc length. Okay, let me just write some intro for arc length, but I don't think we can finish the arc length. So there is arc length. So remember that we can have the Cartesians as in a polar, which convert the x into the polar arc cos theta, or we can write this is with the functions, and we have this y r sine theta. Assume that the a or the theta is between a and b, and it's similar to the parametric. We can set up our dx d theta, but now our r is not a constant but a variable, so we need to set up a product rule. Okay. And then using this, we are going to have plus it's too long. Let me write this. Okay, so we cancel this one canceled with this, right? And this one will be r squared, and the dr over dt will be dr over dt. Okay, assume f prime continue. We can use the parametric arc length. And using theta as our variable or parameter. So that if we have r equal function of theta, and theta is between a and b, then L is The example maybe later on next Friday class. Yes. Yeah, later. Okay, I think I will finish up until here. Okay. Actually, I prepared some feedback question, but I think that's for Friday class. Okay, that's for Friday class. I will stop until here.